This part of the lecture is about the two examples in chapter 1, page 6, and both examples are in relation to the way we solve quadratic equations. Basically, in principle, when you are within the scope of complex numbers, there isn't much change happening from the scope of real numbers, but sometimes technically the way we solve quadratic equations with complex numbers may get rather lengthy. Let's just look at these two examples. The first one is absolutely trivial. The first one is just looks at the equation like this: 5x squared take 4x plus 1 equals 0. And we have to find the solutions of these equations within the scope of complex numbers. Now, from your school, you know that if you deal with any quadratic equation, and I intentionally here use the letter z for the unknown to indicate that now we look at the quadratic equation within the scope of complex numbers. And of course, when you look at the equation like this, it is quadratic when the highest coefficient, the coefficient a, is non-zero. Otherwise, it's no longer quadratic equation. So you know the formula for the roots of such equation. You got two roots. Normally you denote them z sub 1 and z sub 2, and you go with it like you go after these roots like so. You take negative b coefficient, plus and minus, and you compute this discriminant expression, which is b squared take 4ac, and you divide by double a. All coefficients, of course, come from here, from this equation. Now, there is a slight variation to this formula for the solutions of quadratic equations. This variation is useful when you know that your b coefficient is even integer. In this case, you can use so-called half formula for the solutions, which makes your numerical computations lighter. So the half formula, you can compare this half formula with this full formula. Look at this. The half formula says the roots z1 and z2, they are negative b on 2. That's why we call it the half formula. And then you go for the discriminant, but that's the half of the discriminant, or in fact 1/4 of the discriminant, negative b2 square ac, and you have just a in the bottom. Though this formula looks more complex than the original one, in case when you deal with the even number in place of the coefficient b, numerically or computationally, following this formula is easier. And that's what I will do very often. For instance, that's a very good example. Here the coefficient b is negative 4. That's even number. So we can benefit from using this simpler formula for the roots. So let's just do that. So here's my roots, z1, 2 equal 2, which stands for negative b on 2, which stands for this, and your b is negative 4, that's why it's 2, plus minus, then goes your discriminant expression. 4 stands for b on 2 square, this 4, b on 2 square, ac is up here, and you divide by 5, which is a down here. Now, it's a very simple expression, you can finish it easily. 2 on 5 plus minus I came into our consideration because 4 take 5 is negative 1. And that's all there is to this example. Of course, the answer to this question now, the solution to this equation, it's a complex number, and that's a pure complex number. And that's what this symbol indicates. It indicates that it reads, in fact, set minus, and when you see something like this, it means that this number belongs to set C, but does not belong to the set R. The reason for that is just because this is a pure complex number. Okay, That's the first example on page 6 in chapter 1. There is a second one, which is a more involved example, but it's still example about quadratic equations. And this time, that's the equation we have to look at, is this one. That's again a quadratic equation, although some coefficients here, coefficient c, in fact, is now given by truly complex number. Well, this brings nothing but extra computational complexity to the equation. In principle, this is identical to the equation we just finished. So in principle, you do again the same thing. You start off with the formula, and this time my b coefficient is -3, so there is no any point in using this. There's no any point in using this half formula. We have to go for complete formula, and if I go for that, that's what I will have. My b, which is 3 plus and minus, then goes my root. B squared, it's 9, is my b. B squared is 9, and then goes 4ac. A is identity, but c is my complex number 4 plus I, and we have the 2 at the bottom of this fraction. We could simplify this a little bit further. If I simplify this, if I divide every term in the numerator by the number in the denominator by 2, then that will be 3 on 2, that's the first thing here, plus and minus, and then goes 1/2 and the expression under the root. That's it. We just literally applied the formula for the solutions of the quadratic equation to this particular equation. But because my c coefficient was a truly complex number, there is something still yet to be done, because that's the root of this expression. It's a root of complex number, square root of complex number, and this is something we yet have to compute. Right. There will be a few ways how we can find a square root, or in fact a root of any degree from a complex number, but in this case the only computationally workable approach is like so. We take this number, we start off in fact by saying something like this. We start off by saying, let's just look at the identity like this. This is a number from which I have to take a square root. And the square root of that number will be something which, if you square it, that returns your initial number. So this a plus bi, that's the unknown square root we're looking for. So our job is now to identify these two unknowns, a and b. And of course we can always assume, we assume that these a and b are real numbers. Right. A and b are real numbers. What we will do next? We of course do the expansion on the left-hand side here. The binomial expansion. We did this expansion a few times, so I'll do this expansion again. So if I do that expansion, that would be a squared plus 2iab minus b squared equal, that's the left-hand side of the expression, -3, -4i. That's how the expansion of the left-hand side would look like. Pay attention that, you get used to the fact that when you do binomial expansion, the b in the expansion comes with a plus. Here, my b came with the minus because of the imaginary unit, of course. That's the number which, if you square it, gives you negative. That's why you got the negative in here. Now, look at this. Remember, my a and b are the unknowns we're going after. But now you've got a complex number on the left-hand side, unknown, I mean the complex number which involves some unknowns, and some pretty much known complex number on the right-hand side. What you can do, what you can say now is this: if you have two complex numbers which are equal, then you can equate separately real and imaginary parts of each of these complex numbers. This is something which was part of one of the problems earlier in chapter 1, And that's something which I summarize here for you. If you have two complex numbers, a plus bi and a1 plus b1i, and we given that a1, b1 are real numbers, then this identity is equivalent to these two independent identities. Real part on the left-hand side, equal to the real part on the right-hand side, imaginary part on the left-hand side equal to the imaginary part on the right-hand side. So that's what we're going to do here. We're going to identify the real part on the left-hand side, that's a squared take b squared, and equate this to the real part on the right-hand side. Is the result of this action. Similarly, we identify the imaginary part on the left-hand side. Here it is, 2ab. We identify the imaginary part on the right-hand side, and we equate them. Here we go. So instead of looking at this complex equation, we will look at these two separate equations with real numbers only. Now, you probably can devise a few ways how you can solve this two equations for A and for B. For instance, I suspect that many of you will go after the method which is called substitution, but it's something which I personally don't like. In fact, the way I solve it, probably you won't like it at first, but later on you realize it's a very good way to do things in comparison, for instance, to substitutions. So first I'll observe for you that this equation can be transformed into something like this. If you just simply I divide the whole equation by 2, which makes -2 on the right hand side, and then I square this equation, which makes x squared times b squared equal 4. Now, in this form, these two equations, this latest one and this first one, especially if I make this auxiliary substitutions, x1 will stand for a squared and x2 will stand for -b squared. Yeah. In these two equations, the first one up here and this one, yeah, these two equations given this substitution will look like this right away. x1 plus x2 equal -3, and x1 times x2 equal -4. So instead of going after a and b, I'll go after x1 and x2. And when you look at this, you should probably realize by now that this is something which appears in the theory of quadratic equations is called Vieta's theorem. That's a theorem which says if you have a quadratic equation with the unity as the highest coefficient, then the roots to this equation must satisfy these two relations. Some of the roots must be equal to the coefficient next to the z with the opposite sign, and product of that must be equal to the last one with free coefficient. That's the content of Vieta's theorem. Normally, more often, use this theorem from equation down to these double identities, whereas this time we use it the other way around. We use these double identities and we will produce the corresponding equation. So if you look down here, that's exactly the statement. These double identities from the Vieta's theorem, and we see that my x1 and x2, which are unknowns, must be two roots of the quadratic equation like so. In fact, when we're going to solve this, we can easily guess the roots. We can easily guess two numbers such that the sum is -3 and the product is -4. If you just make a little bit of an effort, you will realize x1 must be 1 and x2 must be -4. And you can do double check. Product of these two numbers of 1 and -4 is -4, and that satisfies this. And sum of these two numbers, 1 and -4, is -3. The reason normally when you guess this kind of roots using Vieta's theorem, you can alternate in any possible ways. You can say x1 is -4 and x2 is 1, so the other way around. But in the current setup, you cannot do that. And the reason for that is this, because our x1 and x2 they have extra meaning. And this extra meaning in particular says to us that x1 must be positive, remember? A was a real number, and when you square a real number, the result will be positive. This is not true for complex numbers, by the way. If you square a complex number, the result may be whatever, can actually be any number of any sign, in fact maybe even not a real number. But for real numbers, and that's what we're dealing with here, with A and B, x1 must be positive. That's why 1 was a choice for x1, and the same story goes here, x2 must be negative. And that's why -4 was a choice for x2. Now, of course, we solve. We do back substitution. So we know x1, x2. Now we can compute A and B, and that's how they look. A will be negative or positive 1, and B will be positive or -1. And pay attention, the signs here, the choice of signs must match here. So choice of negative sign for A will go only with the choice of positive sign for B, and positive choice for A will go with the negative choice for B. The reason for that is this relation. This relation in particular tells us that A and B must be of opposite signs. That's the only reason, this is the only chance for the product of two numbers to be negative. And I think that finishes our quest for this root of a complex number, because A and B were the unknowns we were looking for, and now we can conclude that the square root of this complex number, this is exactly my A plus BI, so we have two choices for that, and here they are, plus minus 1 take 2i. In fact, if you remember details about the formula for the solutions of the quadratic equation, this plus minus is in fact already accounted for in this plus minus. And so actually we don't have to do plus minus once again, and now I can finish that this z1, 2, the roots we are looking for, is 3 on 2, that's this first thing, plus minus 1/2, and now for the root goes the expression we have just computed. You can of course open the brackets here, do your arithmetic, and if you do that, you will end up with two roots like so.